All right, everybody, good morning. Hope you're all well. A couple of announcements to begin this morning. The TAs are both going to hold their office hours on the 4th floor lobby of Natural Sciences 1, building Natural Sciences 1. So this is kind of an open, breezy space that sometimes serves the purpose of office hour room. So for the time being, that's where they're going to hold their office hours. In the future, that may change because we're trying to get some dedicated rooms for the use of office hours. We'll see if that pans out. Okay, so but for now, Natural Sciences 1, 4th floor, with the times that are already in the syllabus and on the website. Okay, so with that, let's get started this morning. So we were talking last time about point groups, and I hope everybody has been practicing assigning their point groups. I'm sure it's been that's been very much the case. Uh-oh. That's not good. Unfortunate. Okay, so what I thought we would do this morning is start with a little self-test of point group assignments. And so I show here 4 hypothetical molecules that serve as nice examples of assigning point groups. And of course the decision tree that helps us, if we need it, to make the decisions to assign the point groups rapidly and correctly. What I'd like to do is to take about 2 minutes. You guys try to assign the point groups for these 4 molecules, and then we're going to walk through what we think the answers should be. We'll have a couple of different examples, molecular and non-molecular examples of assigning point groups. So take 2 minutes now and try to work through these 4 examples here, and then in 2 minutes we'll discuss them. At 9:04. Okay, everybody finished? Seeing some looks of confidence, some looks of complete panic in the audience? Okay, so let's walk through these. We'll start here and we'll go counterclockwise. Okay, so let's start with this one here. What do we see about this molecule? Is it high symmetry or is it very low symmetry? That's kind of the first set of questions. It's neither, right? And so what we want to do then is assign the principal axis, the principal rotational axis of the molecule. So what do we think that is? Okay, so we see its C2 axis along the, let's call this the metal-metal bond. That is what M could indicate. So we see a C2 along the metal-metal bond. If we do a rotation 180 degrees, we interchange the B's, we interchange the A's on that side, we interchange the A's, we interchange the B's on that side. Okay? Next question then, perpendicular C2 axes. Are any perpendicular C2 axes present? Okay, so let's see. Let's look at a vertical axis is possible, right? If we had a vertical axis and we did a rotation at 180 degrees, B would go into A, right? So that's not a good rotational axis. Are there any others that are possible, perpendicular to that principal axis? We have to kind of defocus our eyes a little bit. What if you had an axis that was pointed 45 degrees directly between these two atoms here, coming out this way and going in that way? A 45-degree angled axis would rotate B to B, A to A in the front, and A to A, B to B in the back. And so there is one perpendicular C2 axis that cuts right through the face of this plane here, right? Goes this direction. And there's a second one that goes this direction, cuts right through the face of this plane here, these four atoms, and cuts down to the left. So there is a principal C2 and two perpendicular C2 axes.
So in this case it would be diagonal.
It's a diagonal C2 axis, right? It doesn't pass through any of the atoms. It passes between all of the atoms. But that immediately tells us that we have a what kind of point group? A D point group. Okay? And we have specifically a D2 something point group because we know the principal is 2. The principal axis is 2. So then the question becomes one of mirror planes. Is there a horizontal mirror plane in that molecule? Remember, horizontal mirror plane would be one that bisects the metal-metal bond here and that's perpendicular to the C2 axis. And there is not, right? Because if there were, we reflect B into A, and that doesn't work out, for example. And all the other atoms along the square don't work out either. What about what about vertical mirror planes? Those that are along the metal-metal axis. There are vertical mirror planes, right? So we can have a vertical mirror plane that's in this plane here. That reflects A to A and B to B, and all the other 6 atoms here stay unmoved. Okay? And so what we have is a D2D point group in this particular case. It's not D2H because there's no horizontal mirror plane, but we do have vertical mirror planes, so it's D2D. Does everybody see how that's done?
So does it have to be like a the D doesn't have to be like
Yeah, so in the D point groups, you either have an H or a D possibility. There is no V possibility. So basically, D and V are kind of the same idea in the D point groups. Yep. If there's a mirror plane perpendicular to the principal axis, it's horizontal. But if it's along the principal axis, then it's either D or V, right? Yeah. And in the D point groups, it's D. Okay, so D2D is the first one. What about this second example here? What do we have here?
C2.
So do we see a C2 axis in this molecule? Where is it? So again, there's one that goes right through the same way that we showed last time, right? 45 degrees, it comes right down, right? Is there a perpendicular C2 axis in this case? Turns out that there is not. So this is just a C2H. So in this case, we have a horizontal mirror plane. Let me see where it is. The horizontal mirror plane is right between these two atoms, It's a plane that cuts right through here. And it would reflect A to A, B to B, A to A, and B to B. And it's perpendicular to the C2 axis. It's coming 45 degrees out of this plane of atoms here, coming out this way and going in this way. Okay. There's no perpendicular C2, because if there was a C2 axis that we tried to do in this direction, we'd flip 180 degrees and put the B's where the A's are. And there's no perpendicular C2 along the metal-metal bond, because if we did the same thing, this B would go to that A, this B would go to that A, and it doesn't work out. So in this case, we only have a C2 with no perpendicular C2s, and we have a horizontal mirror plane. So that kicks us into the C point groups, and it's a C2H in this case. Make sense so far?
When
So the C2 axis, this plane here that's made up of these 4 atoms, or 3 atoms if you want to just pick 3, the axis is perpendicular to that plane. So it points 45 degrees in this direction, cuts right through that plane, right through the middle of the metal-metal bond, and comes down to the right of the molecule.
Is there not one coming from the other way as well?
From this way, from the right down through the bottom, this way? Well, if you look at that, what do you think? So if you do a 180-degree rotation along that direction, the B's will swap where the A's are. They'll rotate into the A positions, and so you don't have a C2 axis in that direction. So the axis that you're talking about would be this one, right? And if you rotate 180 degrees, these 4 atoms here in this plane that's perpendicular to that axis will rotate 180 degrees around. These B's will be then located where these A's are. So it may be throwing you off a little bit that we're not dealing with just X, Y, and Z, but we're dealing with coordinates, rotational axes that are between the main Cartesian axes. So it's a little bit difficult to visualize, maybe. Do people see that there's only one C2 axis in this molecule? Right? So if it's in this direction here, right, then you have AB, 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 AB. If you rotate 180 degrees, the B's and the A's interchange. Okay. What about example number 3? What do we think about this one? Are there any rotational axes in this molecule? This one here? So if we chose a C4 axis along the metal-metal bond, for example, and did a 90-degree rotation, this A would go there, but this A would go to the B position. So that doesn't work. So C1 is one possibility, okay? So I agree with you that this is a low symmetry molecule. Ci and Cs are the other 2 possibilities. What do we think about a Ci point group? What does Ci have? It has the identity, and it has an inversion center, right? Does this molecule have an inversion center? Does not. Does this molecule have a mirror plane? Where is that mirror plane? How about this plane right here? Right? That keeps these 6 atoms in the plane unmoved, but it swaps the B's and it swaps the A's, and we're good. So this molecule is a CS, a low symmetry example where we only have one mirror plane present, and that's it, other than the identity. Okay? Everybody with me so far? Okay. What about the last example? Question first.
Does the center inversion have to be in the center of the system?
Yeah, for this kind of example, it's definitely right in the smack center of the molecule, yes. And so in general, that's going to be true. Yep. It has to take all of the coordinates of the molecule and swap them, x, y, z to negative x, negative y, negative z. So it has to be in the geometric center of the object.
In other cases, can you pick the center to be somewhere else? Like in between, let's say, the top A and B bonds?
Like here. So this doesn't make any sense to call this an important point in the molecule, because if you tried to invert through this, you would displace the molecule actually, and it wouldn't be a point group anymore, or a point operation anymore. So yeah, the inversion center is going to be at the center of the molecule. What about our 4th example? What is the principal axis of this molecule? So we have a C4 axis. I'll agree with that. The C4 axis is the metal-metal axis. You do rotations, the A's interchange and the B's interchange. Okay? So then the question is, horizontal mirror plane. Yes or no? I'm hearing equal mixtures of yeses and nos. So remember, the horizontal has to be perpendicular to the principal axis, which would mean it's this plane right here that passes right through the metal-metal bond and passes through all of these 4 bonds there too. If we reflect across that plane, the B goes to the A, right? That's not a good symmetry operation. So there is no horizontal mirror plane in this molecule. So we know now that we're either C4 or we could be an S something, right? What about other kinds of mirror planes, vertical mirror planes? Do we see a bunch of vertical mirror planes? There's kind of a ton of them, right? So there should be 4 vertical mirror planes. So you have a mirror plane in this plane, you have a mirror plane perpendicular to that plane, and you also have mirror planes that are at the 45s, coming, bisecting this plane here and bisecting this plane here. Okay. Right away, based on our decision tree, we've fallen here, right? We said there's no horizontal mirror plane. We asked if there are vertical mirror planes. We say yes. That must mean that we are C4V symmetry. Okay. So the trickiest 2 things about these examples are, first of all, we have rotational axes that are not passing between the atoms in some cases. Right? So those can be difficult to see at first. But you need to keep in mind that they can exist, and they're just as important and relevant as any of the other rotational axes. And the other thing that I find particularly difficult is to verify that you have a low symmetry point group when you have a lot of atoms. So you really have to stare at this for a little bit to consider and to convince yourself that you don't have any rotational axes, right? That you don't have an inversion center and so forth. Right. Questions about these 4 molecular examples? Yeah?
So just to clarify, for horizontal mirror axes that go between the atoms, you rotate 45 degrees counterclockwise or 90?
Horizontal mirror. So
That go in between them.
So if you have a mirror plane, you always reflect through the plane. So the coordinate that is perpendicular to the plane goes from positive coordinate to negative coordinate, right? If you have a rotational axis, then you're actually doing a rotation rather than a reflection. Yep. So the mirror planes can be anywhere. So here, for example, there's a mirror plane that's coming out 45 degrees. And that reflects B to B, A to A, and on the bottom here, B to B and A to A. Okay. Yeah. Other questions about this? I promise with practice, you will become experts. It'll be like second nature to do this. Let's look at another example. What is the point group of a baseball? So you can have a lot of fun just going through everyday life and assigning point groups to random objects. It helps to have some symmetry to the object. So, assigning a point group to the chair is not too interesting. It's C1, right? But assigning point groups to other things can be a lot of fun. So what about the point group of a baseball, including the stitching? Okay, so we're not just looking at the sphere, but we're including the pattern that's made by the stitching. And if you have difficulty looking at a baseball and understanding what the symmetry could be for baseball, you could look at a tennis ball instead. It's brighter, and it has exactly the same stitching pattern, right? Exactly the same symmetry. So what do we think about the symmetry of a baseball or tennis ball? So we see that there's a C2 axis, right, in the baseball, the tennis ball. Where is that C2 axis?
Right between the closest points of the stitches.
Yeah. So it's maybe easiest to see because of in the tennis ball because of its rotational orientation. But the rotational C2 axis is coming right through here and passing down that way, coming out this way. Okay? And so if you hold a tennis ball in your hand with the narrow part of the stitching close to you, the C2 axis is coming right out at you. You rotate around that 180 degrees and you get the same object back. So again, that axis is popping out of the board, kind of at a shallow angle in this case, going in and through the center of the tennis ball in this way, okay? Passing between the closest parts of this stitching here. So we have a C2, I'll agree with that. Do we have perpendicular C2s? Does anybody have a tennis ball with them? Or a baseball? I actually looked this morning, and I think my daughter has thrown all of our tennis balls over the fence. So it turns out that there are two, there must be 0 or 2, right? There are 2 perpendicular C2 rotational axes. And you can kind of see it again with the tennis ball easiest. And the rotational axis passes through this stitching and right through this stitching. And also another one right through this stitching and right through that stitching. If you get yourself a tennis ball and put your fingers, one finger here and one finger here, and use your other hand to rotate the tennis ball in your hand, you'll see that after 180 degrees, the tennis ball looks exactly the same. The stitching, remember, this stitching kind of does a funny pattern on the back. And when you rotate it around, you'll see that it in fact is the same object, and a C2 perpendicular is a good rotational operation. I wanted to find also a video, but there were videos last year, but I couldn't find the videos anymore. Somebody had taken them down of actually assigning the point group of a tennis ball. So we have a D2. The question is, are there any mirror planes in the tennis ball? There definitely are mirror planes, right? So there's a mirror plane that cuts the tennis ball in half in this direction, for example, and a mirror plane that cuts the tennis ball in half in that direction. Right? So what's the point group of a tennis ball or baseball then? D2. Is there an H? D2D. Tennis ball is D2D, and here are the different symmetry operations that pertain to that particular point group.
Where was the principal axis?
The principal axis is the one that we chose at the beginning, but it doesn't matter which one you choose. The principal axis is this one that comes this direction and passes through the middle of the tennis ball kind of in that direction. Passes right between the narrow parts of this stitching here. Yep. And so then you have a mirror plane that's parallel to that axis in that direction, and another mirror plane that's parallel to the axis in this direction. That's why it's a D2D and not a D2H.
Show me again where the perpendicular C2
Yeah, this is the hardest part about assigning the point group of a tennis ball, is finding the perpendicular C2s. And it's not totally satisfying to do it in a two-dimensional projection, but it goes from here to here, and it's perpendicular to the principal axis. Okay? And another one goes from here to here, also perpendicular to the principal axis. Yep. Okay, tricky. So you can assign point groups to lots of things, the Eiffel Tower, whatever you want really, right? The pyramids, lots of architecture has high symmetry. Let's get back to molecules. What about, and this is the final self-test example, what about the point groups of these orbitals? This orbital is called what? P what? Px, yep. This is what? That's a d orbital, right? And then, do you know what this is? That's the fxyz orbital. Yep. Let's start with the easiest, the px orbital. What's the symmetry of px orbital? I'm hearing the right answer, yeah. So it's linear, right? This is a linear object. This is C infinity V, right? It has an infinite rotational axis along the x-axis, and it has an infinite number of vertical mirror planes, but it does not have a horizontal mirror plane. So it's not D infinity H, but it's C infinity V. What about the d orbital here? So this is an object, right, with 4 lobes of alternating sign, right? This could be positive and that's negative, so this is positive, negative in the xy plane. Okay. So what's our principal axis in this case? So we would have a C2 axis as the principal axis. And in this case, it's just the most convenient to pick the z-axis as the principal axis, right? If you do 180 degrees, this blue lobe rotates into that blue lobe. This white lobe rotates into that white lobe, okay? And we have perpendicular C2s, right? We have a perpendicular C2 along the y and a perpendicular C2 along the x, right? Okay? And we have mirror planes. What mirror planes do we have? Do we have a horizontal mirror plane? We do, right? So in the plane of this object, we have a horizontal mirror plane. And so that immediately tells us that we have D2H. So we can say that this particular d orbital has D2H symmetry. And this is one of the main reasons that we care about symmetry, because we can assign the symmetry of orbitals. And that is an enormously powerful thing, because then we can understand how orbitals mix, how they make molecular orbitals, and so forth. What about this FXYZ orbital? What does this remind you of? Like if you just look at the blue lobes or you just look at the red lobes. Sort of looks like a tetrahedron maybe. Right? Just the red lobes. You can consider these lobes that are pointing toward hydrogen, for example, in methane, right? So you have these two, and then you have these two red lobes low and 90 degrees rotated. So you might look at this and say, this looks like maybe a high symmetry object, the first example of a high symmetry object that we've seen. If you wanted to tell if it were, for example, octahedral, what would we look for octahedral symmetry? What's the defining characteristic of octahedral symmetry? Octahedral. Icosahedral C5, C4 is octahedral, right? So we have 90-degree rotational axes. Do we have any 90-degree rotational axes here? Proper axes? No, we don't, right? If you had an axis this direction here and you rotated 90, the blue and the red would interchange, which is not cool. So it's not octahedral symmetry. You can't find a C4 axis in this object. What about tetrahedral? What's the defining characteristic of the tetrahedron? C3 and multiple C3s in different directions, right? So what about C3 axes? Do we see any of those? So just imagine that you only have the blue lobes present and that each of those lobes is a CH bond, for example. If you had an axis that goes through this CH bond and you did a 120-degree rotation, you'd rotate these three blue lobes into one another. Then you add the red lobes on if you'd like, and they do the same thing. Right? So you have one C3 axis through there. You have one C3 axis through there. You have a third one coming from the back of the plane of the board through this way, and you have a fourth one this way. So we have 4 C3 axes. That is the defining characteristic of a tetrahedral point group. You could go through all of the rest if you wanted to. It turns out that this is TD. Remember, we have the 3 options, T, TD, and TH. TD is the one that's full tetrahedral symmetry with all the different mirror planes present. And you can see that you have a lot of mirror planes present in this object. Okay?
For the center molecular or atomic orbitals before this one, D2H,
Yep.
for that one, are the C2 axes running in parallel with mirror planes?
Yes. Yes, they are. That's right.
So that is an occurrence where you do have mirror planes running.
That's right, yeah. So this particular example here has mirror planes and axes that have points in common. That's right. Okay, so self-test successful, maybe. Or maybe it gives you an idea that it would pay to study up on how to assign point groups. Okay? What we want to do now is we want to move into some more of the mathematical machinery that we'll need in order to make use of our symmetry classifications to describe molecules in different ways. Okay? So we're going to jump into the mathematical machinery of point groups. And this comes out of a branch of mathematics called group theory. We're not going to derive group theory, but we're going and play with it in detail. What we're going to do instead is use the results of group theory to apply to different chemical problems. If you want more information and a more in-depth description of how group theory applies to chemistry, this book here is a great example, a great reference guide. So this is Cotton's Chemical Applications of Group Theory, and I recommend this very highly for anybody that wants to have more information about what we're going to talk about. So in many cases, what we're going to do is just present the results. If you want the derivations and the proofs and so forth, this is one reference book to look for. There are other books that are mentioned at the back of the chapter, chapter 4, that are also very good, okay, good references. So all of the point groups that we've talked about so far are examples of an algebraic structure that's called a mathematical group. Okay? And the definition of a group is fairly abstract. It's a collection of elements that obey rules, certain algebraic rules. And the rules that these different elements obey give rise to the properties of mathematical groups. And it turns out that these properties are very important for chemistry. Okay? So let's look at the rules that mathematical groups obey. And there are 4 main rules that we're going to describe. So just a caveat here, this is going to be very abstract, and it seems like it takes us away from chemistry totally, but it really doesn't. Just bear with me about one class, one full lecture of describing group theory and how it applies to what we care about. We'll come back then to chemical problems, and it'll become very clear, I think, why it's so powerful. Okay? So the first rule is that every group, in our case, every point group, has an identity operation that commutes with all other members of the group, leaving them unchanged. Remember, our identity is just multiplied by 1. Okay? What does commute mean? Commute means that if you take the identity and some other operation, let's just call it A, and you perform the math in this way, so we do A first and then E, it's the same thing as doing E first and then A. Okay, the order doesn't matter. And because it's an identity operation, it's just multiplied by 1, so acting with the identity operation just gives us the other operation out, unchanged, A, whatever A might be. In this case, A is a symmetry operation. It's a C2, it's a reflection plane, it's inversion, it's something like this. Okay? So commutation means that the order doesn't matter. You get the same result. Okay? So that's the first rule. The second rule of our point groups is that every operation in the set of operations in our point group has an inverse operation that, when combined with that operation, yields the identity. And when we talk about combination, we're talking about multiplication in the matrix sense. So when we do combinations, when we act on a molecule, we're always going to act from right to left. So in this case, we do A first and then E, just like you would do in a matrix multiplication. So the inverse is such that when you multiply it together with the operation, you get the identity. Okay? Let's look at an example of how this works out. In C3V point group, we have these different symmetry operations, 6 operations altogether. Every one of those operations has to have an inverse that gives us identity. So what is the inverse of the vertical mirror plane? Well, it's just simply itself. If you do a reflection and then you do a reflection back, that gives you identity, gives you nothing changed. So the inverse of the vertical mirror plane is itself. The inverse of the C3 squared operation, right, 2 120-degree rotations, is just the C3 operation, which is also in this set. So we do 360-degree rotation and we get identity. So we would say that the inverse of the C2 squared is, or the C3 squared, I'm sorry, is the C3. And all of these inverses have to be in this set of objects in our point group.
Sorry, I think this might have gone over my head entirely, but when we say we're multiplying these operations, what does that distinctly or
I'll show you in just a second, yeah. So I'll show you how we multiply these operations together in a minute. Yep. Okay, so we have the identity, and every operation has an inverse in this sense. The third rule, the product of any 2 operations, that is, any binary product of the operations in the point group, must also be a member of the group. So if we multiply any 2 of them together, we get a third, perhaps, but it's also already in the set of objects. So for example, let's look at a C4V example, which has these symmetry operations present. If we take any binary product, that is 2 things multiplied together, in this case C4, let's multiply that by C4, so we do the C4s twice. That gives us, of course, a C2. And a C2 is in the set already, as it must be to be a complete set. What if we do a vertical mirror, a vertical reflection, and then a C4, well, it's not super easy to see just looking at it, but if you write it down on a piece of paper, you can see that that result gives you a dihedral reflection, which is already in the set. If you do a vertical and then a dihedral reflection, that turns out to give you a C4, which you can prove very easily by just jotting it down on a piece of paper. And of course, the C4 is in the set. And so this is the way that we can actually tell that we have a complete set of symmetry operations in our point group, is that all the binary products have to yield something that's already in the set. This is a way that we can find all of the symmetry operations if we don't already know what they are. So this is sort of a beautiful completeness to these sets of elements. And the fourth rule is that the associative law of multiplication holds. So if we have three operations, A, B, and C, it doesn't matter if we do C and B combined first and then A, or if we do C first and then B and A combined. As long as they're done in the same order, you get the same result. Okay? So associative law of multiplication. It turns out that it's very convenient and powerful to think of this math in terms of matrix multiplication. So we can assign basically a matrix to any individual symmetry operation. And so in order to really understand what we're doing here, we have to review very quickly matrices and matrix multiplication. Okay, the very basics of matrix math. If you are totally unfamiliar with this subject, then there is a little primer that's on the website, Basic Algebra for Matrices, Introduction to Matrices and Basic Algebra. Okay, so we're just going to look at the very essentials here. A matrix is just an array of numbers, and we're interested in mostly square matrices that have an equal number of rows and columns. Okay, and these numbers could be anything. I just throw up here a just totally random example. Okay, a 3 by 3 matrix is what we would call this, or a square matrix. We're also going to come into contact with column matrices. So column matrix is just one in which you have only one column of numbers. And a row matrix is one in which you have just one row of numbers. Okay. When we talk about multiplying symmetry operations, we're talking about multiplying in terms of matrix multiplication. To multiply two matrices together, what we do is we add all of the products element by element of each row of the first matrix with each column in the second matrix. So it's row multiplied by column, adding up all of the different elements. So let's show how this is done by just a 2 by 2 matrix multiplication. Okay, so we're going to take this matrix, which is a 2 by 2, multiply it by this one, which is a 2 by 2. And what we want to do is we want to add up the products of each element by row and then column. So for example, if we wanted to look at the element that's going to be located in the 1, 1 position in the product matrix, we're going to have 1 times 1 plus 2 times 3. So we take the products and we add them together. 1 times 1 plus 2 times 3. Row, column. First row, first column. Okay. So that would give us a number here. It turns out to be 7. Right? What about the next one? Let's just do this one here. This is going to be the second row and the first column. Okay? So 3 times 1 plus 4 times 3. That gives us the value for that element in the product matrix. And we can do the other two. So this is going to be the first row, second column. That's this one here, first row, second column. 1 times 2 plus 2 times 4 gives us that number. And then finally, the second row, second column, 3 times 2 plus 4 times 4 is what we should expect there. Okay. We can then simplify that, and that's what you get for the product. Okay. A 2 by 2 matrix in this case, in which you have, the sum of the products. Okay. It turns out that for almost all of the matrix multiplication that we're going to be doing, what we're interested in is a 3 by 3 multiplied by a column matrix. Okay. This is almost always what we'll be doing. And in this case, if we have a 3 by 3 square matrix multiplied by a column matrix, in many cases we're going to have a very simple 3 by 3 matrix. You do the same prescription, okay, row by column, There's only one column here, and so we would have, in this case, for the first element of the product, we're going to have 1 times 1 plus 0 times 2 plus 0 times 3. That's 1. Okay. The second element here is going to be 1 times 0 plus negative 1 times 2 plus 0 times 3. That's negative 2. Okay. And then the third one down here is going to be 0 times 1 plus 0 times 2 plus 2 times 3, or 6. Okay. That's how we would get the product column matrix from this. Why am I talking about matrices here? Let's show how this can really be a powerful tool in understanding what the symmetry operations are doing. Okay, we can represent every symmetry operation that we've talked about as a 3 by 3 matrix that converts the original coordinates, x, y, z, into the new coordinates after the transformation by the symmetry operation. That's why we call this a transformation matrix. It takes the original coordinates and transforms them into the new coordinates after the symmetry operation is done. To make it concrete, let's consider a specific example, C2H point group. Here's a molecular example of that. Okay, we should be able to quickly tell that this is C2H. Okay? It has a C2 axis right there at the middle point of that bond, interchanges the bromines, and it has a horizontal mirror plane, okay, because the molecule is flat. Okay? Let's assign coordinates, x, y, z coordinates to this molecule. The convention is always to put the principal axis as the z-axis, and then you can put the x and y as the molecular plane. Okay, that's the convention that we will follow. The z-axis is coming out at you, right? Okay. Let's develop transformation matrices, 3 by 3 matrices for each of the symmetry operations in this point group. We have identity, C2, inversion, and the horizontal mirror plane. What does the C2 operation do to the x, y, and z axes? If we do a C2 operation, the x rotates 180 degrees around and it becomes negative x. The y, the new coordinates for y rotates 180 degrees around and becomes negative y. And z is unaffected by a C2 operation because it's happening along the z-axis. Right? So the z just becomes itself, no change. Okay? We can represent this as a 3 by 3 transformation matrix like this. We have elements only along what's called the diagonal of the matrix. Okay? We have a negative 1, which tells us that the x is going to be multiplied by negative 1. We have a negative 1 for y, and we have a positive 1 for z. Okay? Let's see how this works. This is the transformation matrix for C2 in this particular point group. This is how the matrix multiplication looks. In order to get the new coordinates, x prime, y prime, z prime, let's call them, we take the old coordinates, x, y, z, and we act on those old coordinates with the transformation matrix that's here. Just move that here. And that's going to give us the new coordinates in terms of the old coordinates. And so what do we do for x here, for the first element in that column matrix? Negative 1 times x plus 0 times y plus 0 times z gives us negative x. For the second, 0 times x plus negative 1 times y plus 0 times z gives us negative y. And z is unchanged. 0 times x plus 0 times y plus 1 times z gives us z. So matrices are a natural way to show how the coordinate system transforms under these symmetry operations. So that's C2. What about inversion? Inversion takes x to negative x, y to negative y, z to negative z. So the transformation matrix for an inversion operation is just negative 1s along the principal diagonal and nothing else in the other elements in the matrix. And so if we do the same math here for the inversion, we act with the inversion operation. We're going to convert the x, y, z into negative x, y, negative y, negative x, negative y, negative z. Okay. So we've done C2, we've done I. E is just trivial. It's just the unit matrix with just 1s along the principal diagonal. Okay. And we could do the same thing for the horizontal mirror plane. What would the transformation matrix look like for the horizontal mirror plane? It would be 1, 1, negative 1 along the diagonal of the matrix. So the only axis that's going to change in a horizontal reflection is going to be the z-axis. The x and the y coordinates don't change. Okay? And that would be our 4 transformation matrices for this point group. Okay? So here they are. Here's the 4 transformation matrices, and we're going to, we have about 5 minutes, so should be able to reasonably describe this. So here's for the identity, here's for C2, here's for inversion, and here's for the reflection. Okay. One of the things that we can immediately do is show that matrix multiplication gives us the exact same answer that we know intuitively if we multiply 2 of these operations together. We know that if we take a C2 and we then do it twice, that we're going to generate the identity. Right? The molecule is reflected on, or is rotated 180 degrees and then rotated 180 degrees back, so we've done nothing. And matrix multiplication better give us that answer. And it does. So if you take this matrix for C2 and multiply by a second matrix for C2, you can convince yourself that you're just going to have the unit matrix 1, 1, 1, which is E. Right? That's the matrix for identity. Okay? So it really works in any arbitrary sequence. Now, what we want to do is we want to take the information that's buried in these matrices and we want to tabulate it in a very convenient way for reference. We're going to develop what is called a character table for this point group. Okay? So what do I mean by that? If you look at these transformation matrices, you see there's only values along the principal diagonal. If you take the sum of the values along the diagonal, this is called the character of the matrix. In math, it's called the trace of the matrix. So the trace is equal to the character. Okay? So the sum of the numbers along each matrix diagonal is called the character in our description. And it gives you basically a shorthand version of the matrix representation. So you don't need to know all of the zeros in this 3 by 3 matrix in order to get the essential symmetry information out of what the identity operation does. All you need to know is the sum of the diagonal here is 3. That tells you in another way, a simpler way, what the symmetry is of that particular operation. So we take the sum, that's called the character, and for E, we would have the sum giving us 3. Okay? So we would have a character of 3 for the identity operation. That's how we would describe that in words. If we looked at C2 and we did the sum, we're going to have -1. So the character for the C2 operation is -1. Character for the inversion operation is -3. The character for the reflection operation is 1. Okay? And so what we've done here is we've condensed the transformation matrices, all of these numbers, that's just redundant information, into simple 4-number set. Okay? That contains all of the information up there in the transformation matrices. This thing here, this list of characters, is called gamma. This is called a reducible representation of the transformation matrices for this point group. It's reducible in the sense that we can divide it into simpler components, as we'll see maybe next time. Okay? But what we would do is we would list the point group, we would list the symmetry operations for that point group, and in this case we would say that we have a reducible representation with a character of 3 for E, -1 for C2, -3 for inversion operation, and 1 for the reflection. We'll show next time how we can break the reducible representation into irreducible components and build the entire character table for this particular point group.